right? And you can turn your videos on. Um, so what we're going to do today is we're going to do a review of a problem set at the end of chapter 7. We'll review the things that we covered last time, and then we're going to go right into chapter 8. Right? And I believe I have a problem set for chapter 8 too. Just give me a second here. Let me just check something. Let's see if I have that. Yeah, here we go. All right. So it looks like we have both chapter 7 and chapter 8. So, all right. Anyway, let's go share. So share that PDF that I've created for the chapter 7 problem, and then we'll go right to the problem in the ebook. Problems in the ebook. So we're going to be looking at problems 4, 5, 6, and 7. They all refer to the same problem set. So actually, let's sharing this, and let's go right to the ebook. All right. All right, so this is the exercise at the end of chapter 7 in the ebook. And so let's take a look at number 4. It says, suppose the scores on a recent exam in your statistics class were as follows. So they gave a bunch of these scores, okay? And I believe there's 28 of these scores altogether. And it says to create a stem plot for these test scores using each tens value once on the stem. So each of these numbers are 2 digits long. The tens value, of course, is the first number for each of these numbers, and the ones value is the second one. You all know about tens and ones for our number system. And so if you look at all the numbers, just scan them, you can see they go all the way from 32 all the way up to 98, right? Just do a quick scan. You see 32 is the smallest number, 98 is the largest number. So when they say create stem, what they're referring to is look at the tens digits, and you're going to start at 3 and just keep adding 1, do 3, 4, 5, 6, 7, 8, 9, like that. So I'll show you what that looks like. Go back to the. All right. So this is the way I presented it. So 3, 4, 5, 6, 7, 8, 9. These are all the tens digits, all the 30s, there's 50s, 60s, 70s, 80s, and 90s. And then each of the numbers to the right of this vertical bar represent the particular number, the ones digit for particular numbers. So there's 32. So that's how you read it, 32. There's no numbers in the 40s. There is a 55. There are 6 numbers in the 60s. Go back, let's just go back to the data set again. All right, and let's go back to that. All right, and you can see if you just scan the numbers here, there's 32 here, there's a 55 here, but there's nothing in the 40s. You'll just scan quickly, there's no 40 anything, all right? So the next one would be the 50s, and there's a 55, right? There's only one number in the 50s, this is the 55. And then the 60s, we have a 60 here, we have 62, 64, 60, there's 2 64s, 61, and 68. All right. What we're doing is just displaying those numbers on this stem plot. Okay. And I put them in numerical order just so it'll be easier to answer questions. So instead of putting them in the order that I see them, I put them in numerical order. So there are 6 numbers in the 60s. There's 60, 61, 62. There are 2 64s and a 68. Does everybody understand how to read this? that I've seen people when I've done tests in the past, maybe they just don't come to class or something. They always, when I ask what the numbers are, they'll say, oh, 2, and there's the number 5, and there's another number 5. No, that's not how you read it. It's 32, 55, 60, 61, 62, 64, 60. You get the idea? I hope you all do. And then for the 70s, if you go back to the data set, there are 8 numbers that are in the 70s. And I put them in numerical order. 73, there's 2 75s, there's a 76, 2 78s, 2 79s. Same thing with the 80s. There's two numbers that are 80s, or 80. There's an 82, 83, 84, 85, and 88. And then in the 90s, if you scan the data set, you'll see there's a 90, there's a 92, 93, 95, and 98. So if you added all these up, all right, if you just counted them, you can find out there's 28 numbers. That's how you double check to make sure you have them all. So here's the point. On a test, if I give you a data set, I might give you the data set in the form of a stem plot, as opposed to just listing the numbers. First of all, it's better organized this way. You can see the numbers more clearly than if they were just in a list on a page. So if I were going to ask questions about this data set, I could present it as a stem plot. That's the whole point. All right. And I would put the numbers in numerical order so that if I ask questions about something like the median, the mean, the median, things like that, you'd be able to figure it out. So anyway, that's what the part A, if we go back to the problem in the ebook, let's go back to the ebook. They wanted me to stem plot where along the stem there would just be one of these stem values, 3 up to 9, and then they said, all right, part B, create one where you have 2 stem values for each of the tens digits. So what does that mean? Let's go back. Let's look at the solution for that, and this is what it means. Basically, you could create a stem plot that looks like this, where you repeat the same stem twice, but you have a lower stem and a higher stem value. What does that mean? That means that for the 30s, you could have, for the lower 30s, you could have you would list any numbers from 30 to 30 through 34. And for the higher values, it would be from 35 through 39, like that, right? And sometimes you may want to do that so that the numbers are more spread out and you can see patterns better. So anyway, 32 is the lower 30s. 55 is the higher 50s, right? Because I said the higher would start from 5 all the way up to 9 for the numbers on the right. 60s have both lower and upper. Here, the 60s have 60, 61, 62, and there's 2 64s. And there's also a 68, which would be in the higher group. And then for the 70s, we have a 73, which is the lower group, and then we have numbers in the upper group. Same thing with the 80s and the 90s. All right, so I hope you understand how that works. And of course, I explained it on the side here. All right, so this is pretty much what they were looking for. But again, on a test, I'm not going to ask you to create one of these. I'll give you one of these, but you should be able to read it, be able to know what it means. All right. Now, the next question they were asking, go back to the ebook. Next question they're asking, part C, is compare those 2 stem plots. Are any features of the data apparent in one of them, but not in the other? Well, let's go back to my solution. And if you look at the first one, you see all the numbers are sort of crammed together. There's even though you could see that most of the numbers are higher numbers, there was not much difference between the 60s, 70s, 80s, and 90s. But if you did the second plot, things are more spread out. And one feature that I did see was that the 32 seems to be definitely what we would call an outlier, a number that seems to be different than, quite a bit different than all the other numbers in the data set. Seems to stick out more here than it does here, right? Sort of see that it's different, but it doesn't seem that far away from the other numbers. But in this stem plot here, it does certainly seems far away. All right, the 55 doesn't. 55 seems close to the other numbers, but the 32 certainly doesn't. So it's one advantage of displaying the stem plot this way is that you could see the 32 as being an outlier, or it seems like it's an outlier. All right. Any questions about stem plots and what, how to read a stem plot? And again, if I give you a stem plot and I ask you questions about it, such as what is the average of the numbers, I think you'll be able to see the numbers better. If I ask you, for example, what the median is, the median, you should be able to figure out. Remember last time I think we talked about the median. It's the middle value, right? Now this is we have it in order here. The numbers are displayed in order from the smallest to the largest. So if we wanted to find the median, we know there's 28 numbers in the data set. And if you remember, I gave you that little formula. Just take the number of numbers in the data set, add 1, and divide by 2. So if we have 28 numbers and add 1, that's 29. Divide by 2, that's 14.5. So in this case, we would average the 14th and 15th numbers in the data set. So you just count till you get to the 14th, 15th number. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so the 14th number is going to be 78. Be careful, it's not 8, it's 78. And the 15th number is 79. So we average those two numbers, we get 78.5, and that's our median. Okay, that's how you calculate the median. All right, so displaying it this way does help you find things like the median. Okay, any questions about that?
Can you, I want to write that down again. Can you explain that, the median?
Median is the middle value.
No, I understand that, but on
Well,
this stem, I'm
there's
really
an
trying to
even
understand this.
there's an even number of values in this data set. There's 28 of them. Remember, when we have an even number of numbers in the data set, we average the two middle ones. If there's an odd number, like 29 numbers, we would just find the middle one. And the way to find those middle ones is simply use the formula, the number of numbers in the data set plus 1 divided by 2. Okay?
All right, the number.
Yeah. And
you said divide. Wait a minute. You said the number in the set
plus 1
in the set,
and then
plus
that sum you divide by 2.
All right. Okay.
All right. And what that gives you is the position of the middle value, position of it. So in this case here, when we take 28, add 1, and divide by 2, we get 14.5. Now, you'll say, well, 14.5 is not a position, but 14 is the 14th number. And the 0.5 tells you to go to the 15th number also. So the 14 and the 15th number, we just count them until we find number 14, which is 78. We just count down until we get to the 14th number, 78, and the 15th number, 79. We average these two. 78 plus 79 divided by 2 is 78.5. Okay, that's the rule for finding the median, is to find the two middle values and average them. If the number of numbers in the data set are even. If there's an odd number of numbers in a data set, then it's just the middle value. For example, if there's 29 values in this data set here, you would have done 29 plus 1 divided by 2, which is 30 divided by 2, or 15, and you would have just simply picked the 15th number in the data set. You would just count it down until you found the 15th number, and that would have been your median.
Why do you add 1?
I'm so confused.
It's just a formula. That's all. It's just an easy way of finding the middle value. That's all.
Okay, so just
don't
to
worry
clarify,
about the why about it. It works. It works.
Okay, so you find the two middle numbers.
If you had
and divide 2.
Yeah, it's just an easy way to find it. In other words, if you have a big data, let's say you had 1,000 numbers in your, not 1,000, let's say you had 885 numbers in your data set. Where is the middle number? Which position is that middle number? Well, that formula helps you find it, that's all. Now, if you only have 5 numbers in your data set, it's easy to find the middle value because it's the third number, right? If you order it, it's the third number. But with 28 numbers, you may have trouble finding it. So it's a formula that works. And what is that?
So,
Okay, go ahead.
so you're saying, okay, so take all the numbers.
Order, it's already ordered for you. That's what I'm
Right.
telling you. If I'm gonna give you a data set, I'll give it to you as a stem plot. It'll be ordered. You don't have to order it. And you
Right,
just,
I'm trying to learn a formula. So you said take all the numbers, add 1.
yeah. Just
So count all the numbers, add 1.
and divide by 2. And that will give you the position of the middle value or middle values.
Divide by 2, but I heard you say something about a 14 and a 15. That's where I'm lost at.
Because that is if there's 28 numbers in the data set, 28 plus 1 divided by 2 is 14.5.
28 plus 1 is 29. Divided by 2 is what?
14.5.
Okay, 14.5. Okay.
And the 0.5 is telling you, take the 14th number, which is the 14 part of the 14.5, and then go to the next one, which is the 15th number.
Then that's going to be the median.
The median is the average of those two numbers.
The median is the 15th number?
No, it's the average of the 14th and 15th. Let's talk about it later. It stays.
So when you're saying the average, what do you mean?
It means average. It means add them and divide by 2.
Right.
Average,
Okay.
average things. Average. Average means to add things up and divide by the number of values.
I'm not getting the 14, 15 average. That's what I'm asking.
No. Why don't you stay behind at the end and I'll explain it to you. All right, because I have to move on. Yeah, let's just. I'll spend 5 minutes with you at the end and explain it to you. All right. All right. Good. So anyway, that is the stem plot. Now let's get to the question 5. Let's go out of here back to the. All right. So we're referring back to the same data set, and it asks you to create a histogram. Now, I'm not going to ask you to create a histogram, but I want to show you how I've created it so that you understand what I've created, so that when you see it, you can interpret it. All right, that's the whole idea. So, because it's saying create a histogram, explain how I came up with it, and comment on the shape. Now, I'm very familiar with how to create histograms because I teach this in my Stat 1 course. And if you were taking Stat 1, you would have to know how to create one yourself using a calculator. But you're not going to do that in this course. You're going to see one that I give you and then answer maybe a couple questions about it. So let's take a look at what the histogram for this data looks like, the one I've created at least. All right, so let's go back to. All right, if you could put yourself on mute, please. Unless you have a question, that would be very helpful. Thank you. All right. Now, what I did, and again, don't worry about how I did it. I did it. What I did was I created what are called 6 classes. Classes are intervals. Intervals of what? Intervals of values that start from the smallest and go up to the largest number. So what I did is I took the data set and divided it into 6 equal pieces. All right. I started off with the smallest number in the data set, 32. And then what I've done, I've added 12 for each of these intervals. You can see 32 plus 12 is 44, plus 12 is 56, plus 12 is 68. Keep adding 12 like that. So I created 6 of these intervals. All right. Now I'm again experienced in creating histograms. It said, why did I do this? Because I know based on the data that I'm looking at, that 6 with 6 of these classes or would be good to display. It would show the trends that I'm looking for. Right? You don't need to know how I did it. But the important thing is that's what I did. Now, how do I read this histogram? Well, again, along the x-axis is the numeric data, but it's classified in intervals as opposed to being classified as individual numbers. All right. We know there's 28 numbers in the data set. Along the y-axis is what's called the frequency. It's just counting the number of numbers in the interval. For example, I have the frequencies running from, and I hope you can see here that each notch represents 1, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay? So the way this works is any numbers in the data set that are between 32 up to but not including 44. Right, so if there's a number in your data set that's 44, it's going to be included in the second class. We call these classes, by the way. So there are 6 classes. Class number 1 is this class. It goes from 32 up to 44. The second class starts at 44, goes up to, but does not include 56. The third class starts from 56, goes up to, but does not include 68. And the fourth class goes from 68 up to 80, but does not include 80. And then the fifth class goes from 80, goes up to, but does not include 92. And then the sixth class goes from 92 up to 104. So what this histogram is showing is that the height of the first class is only 1. That means there's only one number that goes from 32 to 44. And we know what that number is, right? It's that 32, right? So that 32 is in class number 1. From 44 to 56, there's also one number. That's that 55, right? If we scroll up, you see there's a 32, and the next number is a 55. So the histogram showing there's one number between 44 and 56. There are 5 numbers that go from 56 to 68. Again, we can scroll up. And actually, let's look at this histogram over here. Well, actually, maybe it's easier to look at the second stem plot. So from 56 to 68, I believe that's what it is. But remember, 68 is not included in this class. It's included in the next one. So it goes from 56 up to, but does not include 68. I'm saying there's 5 of those, and let's make sure there are. So that would include 60, 61, 62, 64, and 64. These 5 numbers here all are in that interval. All right. And then from 68 up to, but not including 80, we have a 68 here. And then we have a 73, and then 75, 75, 76, 78, 78, 79. These are all in that interval. So there's 1, 2, 3, 4, 5, 6, 7, 8. I believe there's 8 in that interval. 1, 2, yeah, there's 8 of them. And so the height here is 8. You see it goes across here, 8. From 80 to 92, I say there are 9 of them. All right, 80 up to, but not including 92. And we go 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, these 9 here, from 80 through 90. And then the last group is from 92 to 104. And the 92, there's 1, 2, 3, 4 of those. And you can see the height of this one is 4. So this is a way of displaying data where we have classes on the bottom, different number of classes. There are 6 of them. For class 1, 2, 3, 4, 5, 6. The classes are just intervals, and we're just counting the number of numbers in the data set in that interval. All right. Now, what is the thing that we see from this histogram straight away? Is that the data seems to be mostly on the right, and it flows and tails off to the left, right? It seems that that's the way it is. So we could have like we drew a curve around this, it would go like this. So I would call that skew to the left. Remember, the skewness is to where it tails off. where the tail, so most of the data is on the right, but it's skewing to the left. And one of the properties, by the way, of skew to the left is that the mean is going to be less than the median. And the reason for that is that we have these unusually small numbers, the 32, for example, is small, also the 55. And when we do the mean, when we calculate the mean, which is really adding all the numbers up and dividing by 28, because there's 28 of them, the mean is going to be lower because of those smaller values. Lower than what? Lower than the median. Remember what the median is, right? In this case here, it was 78.5. Okay? If we had replaced the 32 that's in the data set with a bigger number, let's say with 40, or even with the number 50, let's even make it bigger. Let's say I'm going to replace the 32 with the number 50. The median would still be 78.5. It'd still be that number in the middle, but the mean would be larger because we would have a bigger number adding into our calculation of the mean. So the point is that the mean is affected by these so-called outliers because we're adding them in. The median is not. The median is unaffected by the outliers because the median's in the middle. So when we have a data set that like this, where it's skewed to the left and we have unusually small numbers, the mean will typically be less than the median. All right, that is what you need to remember, something like that. All right. Now, any questions about that? Now, if you had the opposite situation, where the histogram had most of the numbers to the left and it tailed off to the right, that would be called skew to the right. And then in that case, you would have unusually large numbers that would be making the mean bigger than the median. Again, these unusually small or large numbers does not affect the median, but does affect the mean. So when you have skew to the right, so in other words, if you picture this sort of flipped a bit, this histogram, where the rectangles were larger on the left and smaller on the right, and you just tailed off to the right, the mean would be larger than the median. If it was sort of symmetric, where it was sort of bell-shaped, like we're going to talk about today, then the mean is approximately the same as the median. They're about equal to each other. All right, so that's what the types of things that we ask you to interpret when we talk about when we use a histogram. And you can see the histogram does a really good job of showing this skewness to the left, as opposed to the stem plot. Neither one of these stem plots does a really great job. I mean, you could sort of see it here, right? You could see that most of the data is to the right and it tails off to the left. But I think visually, the histogram does a better job of it. And that's why people use histograms. Stem plots are only good if you have a small data set. Histograms, you can have a very large data set. You can have thousands of numbers in your data set, thousands of observations, and you can still create a histogram. The histograms are very good to do. And you see in real life, many people use histograms. Now, one thing that you could also do, instead of having with the frequency over here on the left, sometimes they have along the vertical axis, they have what's called relative frequency. What's the relative frequency? It's the frequency divided by the total number of observations in the data set. So, for example, the relative frequency for the first class, which is 32 to 44, we have a frequency of 1. It would be 1 divided by 28. We would just calculate that decimal, 1 divided by 28, and that would be the relative frequency for class number 1. All right, so you just take your frequency and divide by the total number of observations, and that gives you the relative frequency. Now, if you did that, it would look exactly the same. The histogram would look exactly the way it looks now. It's just what would be shown on the vertical axis would be the relative frequency as opposed to the frequency. Okay? All right. Now, problem 6 does ask you to find things like the median. I mean, I talked about it a minute ago. So part A, 6A, asks you to find the median and ask you how you came up with it. Well, I wrote it down here because when I post it, and Anika, you had mentioned how do we do this? So it's explained here, but again, stay behind and I'll explain it again. But I explained it all here, how to find the median in your data set, all right? So I gave you all the rules here that you need to follow to be able to do that. Okay, so that's how I show you how I came up with to the 78.5, right? The mean, I gave this little formula here. They do show formulas at the end of each of these chapters. This kind of wiggly looking symbol here means sum. So when you see this symbol here, it just means and then has the X afterwards. The X represents the variable. So it's what it's saying to do is add up all the numbers for that variable. So this says add them all up, and the small n in the denominator says that's the number of that's the sample size. That's the number of numbers in the data set. So when I add up all the numbers and divide by 28, n is 28, I get this number, 76.0357. I'm rounding it to 4 digits when I do it. And what's interesting, I did say this is skewed to the left, and I said in many instances, the mean will be smaller than the median, and it is. The median is 78.5, the mean is 76.0357, and it's smaller, which is an indication that the data is skewed to the left, all right? And the reason for it, this unusually small value of 32 is making the mean smaller. It does not affect the median, so the mean will become lower than the median because of this low value of 32. Now, the standard deviation, there's a formula for it. It's at the end of the chapter. If you have a TI-30X calculator, there is a feature on it, a stat feature. And if you have that calculator, and most of these calculators now, scientific calculators, have this, but on the TI-30X calculator, the third column, the third button down, it'll say data, if you see the data there. And I don't have the ability to display this calculator, but I can just briefly explain it to you. And if you want to, it's really up to you. You can learn how to enter the numbers of a data set into your calculator, and then it'll automatically calculate the mean, and it will calculate the standard deviation, which is very nice. All right, it'll do it for you. So it's worth the effort to Google how to do this, and I think there are videos out there which will explain how to do it with the TI-30X. And if you have another calculator and you're able to enter data, then you can do the same thing. But in this calculator, there's that data button, and just above it, it says stat. So if you hit the second button, the first button on the top row there, and that data button, it'll bring up the stat screen. And then what's underlined there, it says one variable. In most cases, that's all you're going to be dealing with is one variable, and you just hit the enter key for the one variable. And then that'll take you to the stat screen, basically. You're going to be in the stat screen. And then if you hit your data button once again, then it's going to ask for, it'll say X1. And what it's asking for is the first number in the data set. Now, you don't have to put the numbers in order. If the data set's not in order, it doesn't matter. The calculator can figure out the order. But again, if I'm giving you the stem plot where the numbers are in order, just put them in order. And so, for example, the first number of the data set's 32. I would type in 32 and hit enter. All right. And then if I use the bottom arrow key on my calculator, it then has FRQ, which means frequency. And you can actually, if there's more than one of that number in the data set, you can actually put in something other than 1 in there. You could put 2, which means there are two numbers in a data set that match that number. In this case, there's only 132, and then I would just hit the down arrow key, and then it'll give me x2. And I can put 55 in there. I can hit the down arrow key. Again, there's only one of those. I would hit the down arrow key again, and then x3, and so forth. So if you run into, as you're entering the numbers, if you run into any numbers that are listed more than once, then you can just change the frequency to the number of times that it's repeated. Once you've done all of that, then once you've entered everything, then what you can do is hit the Stat VAR button. And when you do that, that's to the right of the data button. And it'll give you several statistics there. It'll give you, first of all, give you n, which is the number of numbers in a data set. And then next to it, it says x with a bar above it. That's the mean. And then right next to it has s with an x next to it. That's the standard deviation. All right. The last one is a population standard deviation, which most likely I won't have to use. So the first three numbers are usable. The first number is the number of numbers in the data set. The second number is the mean. The third number is the standard deviation. Now, once you're done with the stat feature, right above the Stat VAR button, it says exit stat. You would just hit the second button and hit the Stat VAR button, and you're exiting out of the stat feature of your calculator. But once again, if you want to review how to do this, it would save you some time. And you just, again, Google this calculator and Google the stat features of it. And there might be some videos out there which will help you review this so that you can do this on your own. All right, it's not required to be able to do this, but it'll make it easier for you to do. So that's what I did, and I came up, when I entered all the data in, I came up with a standard deviation of 14.1878. That's what it's asking for. So it is important, if you can, to learn how to use your calculator and let the calculator calculate the standard deviation for you. But there is a formula at the end of the chapter. It's a little complicated, and the book doesn't really explain how to use the formula. So if you do not figure out how to use your calculator to calculate the mean and standard deviation for you, then you probably want to send me an email or something, and I will show you how to use Microsoft Excel, which will also do this for you too. All right. So if your calculator doesn't do it, or if you're confused by the videos that you see, then I will teach you how to do it with Microsoft Excel, which I think most of you probably have on your computer. Now, the next question is they ask about the if the number 32 is removed from the data set, what happens to the standard deviation? Well, the standard deviation, the way it's calculated, once we've calculated the mean, what we do is we take each number in the data set and we subtract the mean from it. That's called the deviation from the mean, and then we square that number. And then we add up all those square deviations for every single number in the data set, and we divide by what's called the number of numbers in the data set minus 1. All right. Now, why do we subtract 1? It's a statistical reason. Again, we don't need to go into that, but that's the formula. And that's called the variance when you do all that. And then we take the square root of the variance to get to the standard deviation. That's if you were doing it the long way. Now, here's the point. The standard deviation is affected by outliers, because if we took the mean and we subtracted the mean from 32 and squared it, that would be a relatively large number. If 32 was a bigger number, it was something like 50, then 50 minus the mean would be smaller. So the point of the matter is the standard deviation is affected by the outliers, just like the mean is. And if we remove the 32 from the data set, then what happens is the standard deviation will become smaller, I think. Let me think about that for a minute. Yes, it will become smaller, because the deviation that 32 is involved with, 32 minus the mean squared, that is a relatively large number. If we remove it, the standard deviation will become smaller. And that sort of
I
makes
can't hear
sense.
you, Professor.
I'm sorry? Can you hear me now? So when the 32 is removed, the data set will, the spread of the data set smaller, and we would expect the standard deviation would also be smaller. Okay, that's what they're referring to there. And then number 7 is asking about quartiles. Okay, what are the quartiles? Quartiles, what the median does is it splits the data set into 2
Excuse
equal
me,
pieces.
Professor. I can't hear you at all.
All right, how
I
about
just see
everybody
your
It
else?
might
lips
just be
moving.
you because I would say I
Can't
can
hear you at all.
You can't hear me?
Now, there it go. There it go.
I'm going in and out a little bit.
Yup, you going? I didn't hear nothing you said at all.
How about Aaliyah?
It might just be where she is because I can hear you perfectly fine.
It must be hers then. You can hear me all the way through? Okay.
Now
I think
I can hear you. I can
all
hear
right,
you now.
Nika, I think it's from your end that's causing that. But again, the video, when you can listen to the video again, because it'll be clear.
Okay.
All right. Now, problem 7 has to do with the idea of quartiles. What quartiles do is that they split the data set into 4 equal pieces. So Q1 is, now I'm using the symbol Q1, but Q1 is the lower quartile. It's where 25% of the data is less than that. And Q3, I'm calling that the upper quartile. That's where 75% of the data is less than that. Okay. Now, how do you find Q1 and Q3? Well, the median, remember, is the middle value. And the median means that 50% of the data is less than that number and 50% is greater than that number. So what the median does, it splits the data set into 2 equal pieces. And of course, it's an ordered data set, right? It's from smallest to largest when we say that. So the smallest half, if we found the median of the smallest half, that's called Q1. That's the lower quartile. And that's how you find it. So you find the median first, and then you have the lower half and the upper half. That's what the median splits the data set into. The lower half, if we found the median of the lower half, that's called the lower quartile, or Q1. If we took the upper half and found the median of the upper half, that's the upper quartile, that's called Q3. And that's literally how you find Q1 and Q3. Okay? So in this problem here, the median is 78.5. There's 14 numbers that are smaller than the median of 78.5, and there's 14 numbers that are bigger than the median 78.5. Now, of the 14 numbers that are smaller than 78.5, the median of those 14 numbers is what? It's 64. Now, how do I know that? Because if there are 14 numbers that are less than 78.5, I'm going to use that little formula again. I'm going to add 1 to 14, divide by 2, and it gives me 7.5. The 7.5 tells me that it is the 7th and 8th numbers in the lower half of the data set that I'm going to average. Okay. Now, if you go all the way back to the stem plot and go down to the 7th and 8th number, so it's 1, 2, 3, 4, 5, 6, 7. Did I do that right? 7th and 8th numbers. Let me make sure I'm right about that. Did I say that right? Yes, 7th and 8th numbers. And I think I might have done this incorrect. I'm going to have to change. I'm going to have to correct this because I think I might have done this wrong. So 1, 2, 3, 4, 5, 6, 7, 8. All right. So I did do this wrong in the handout, but I haven't posted this yet. The handout, actually, I must have been sleepy when I did this. So the 7th number in the data set is 44. It's the second, excuse me, 64. 64. 1, 2, 3, 4, 5, 6, 7. The 8th number in the data set is 68. If I average those two numbers, I will get 66. So there's a mistake that I made here, and don't worry about it. I will correct it on this sheet. I'm going to do this sheet and correct it for you. So don't worry about it. So the answer to this question should be 66. It should be 64 plus 68 divided by 2, which is 66. In a similar way, we're going to average the 7th and 8th numbers in the second, the 14 numbers that are bigger than 78.5. So let's go back to the data set. 78.5 is I'm sorry, did I say that wrong? Yeah, 78.5 is between these two numbers here. So the first number that's bigger than 78.5 is 79. So 1, 2, 3, 4, 5, 6, 7, and 8. 7th and 8th, right? 7th and 8th. So first number after 78.5 is 79. 1, 2, 3, 4, 5, 6, 7, and 8. So the 7th number is 85. The 8th number is 88. Put that down. All right. So what did I say it was again? 88 and 85. And again, I did this. I must have been sleepy. I did it wrong. So, so it would be, let me go back again. It would be 78.5. It would be 1, 2, 3, 4, 5, 6, 7. It would be the average of 85 and 88 would be the Q3. And again, I made the same error here for some reason. I don't understand why. And then that should come out to some number other than this, but you're averaging those two numbers. And then they ask you to create what's called a 5-number summary. The 5-number summary will have the median on the top here. We'll have the Q1 and Q3 here. Now, again, I calculated them wrong, but let's just assume that they are these two numbers, but I will correct them later. And then the smallest number in the data set and the largest number of data set are displayed here. Then you create what's called a box plot. Now, a box plot is a visual display of the 5-number summary. Now, the box plot, the way you draw it is you draw a number line that goes from the smallest to the largest. And here I just started with 30 and went up to 100. And what I'm doing here is drawing a box where the left side of the box here corresponds, if you just go down to the number line, corresponds to the Q1, to the lower quartile. And then the right side of the box corresponds to Q3, which is the upper quartile. The line in the middle here, the vertical line in the middle, will be your median. Now, outside of the box here, we draw what are called horizontal lines. Sometimes these are called whiskers, because they look like cat whiskers. And what you do is you draw the horizontal line from the upper quartile up to the largest number in the data set. As long as there's no outliers, you would draw it up to the largest number, which is 98. And then here, you would draw typically down to the lowest number. But notice here, I'm not drawing it down to the lowest number. I'm drawing it down to the next to lowest number, which is 55. Notice way down here at 32, I have an asterisk. Now, the question is, why did I do that? Why didn't I just draw the horizontal line all the way down to 32? The reason is because 32 is an outlier. And according to the book, you need to calculate the outlier. All right, you need to calculate if a number is an outlier. Now, how do we do that? Now, again, I apologize. Q1 and Q3 here are not correct, but I will show you in essence what we're doing, and I will correct this and post it with the correct numbers later today. Now, what we have to calculate first is what's called the interquartile range. Now, I want to distinguish two things about the idea of a range. The range of the number, not the interquartile range, but the range is the largest number minus the smallest number. That's called the range. All right, that's one way of calculating the variability of the data set, how spread out the data set is. So the range is 98 minus 32, which is 66. That's called the range. The interquartile range is actually the distance from the upper quartile to the lower quartile. It's if you subtract those two numbers, it gives you the interquartile range. And the abbreviation for the interquartile range is IQR. IQR. It is Q3, this number, this is the Q3 number, minus Q1, which is this number here. Now, once again, as I said, those numbers aren't correct, but just follow along. Assume they're correct just for the time being so you can understand what I'm doing. So when I subtract those two numbers, I get 20.5. Then what the book recommends is we take this 20.5, this IQR, and we multiply it with our calculator by 1.5. So that's what we're doing here. We're taking the 1.5, multiplying it by the 20.5, and we get 30.75. That's what the calculator says. So you can follow along with your calculator if you like. Now, what do you do next? The next step, and again, this is like a recipe, all right? You know, you cook something, you bake something, you follow a recipe, you're measuring things, you're taking half of this and 3/4 of that, whatever. We're doing the same thing here. This is a recipe. So IQR, we calculate it, we multiply it by 1.5, and then the recipe says that we take this number 30.75, this 1.5 IQR, and add it to the upper quartile. So we take the 84.5 and add 30.75, and we get 114.75. And why do we do that? Is because we're looking for, in this case, large outliers. And the rule says that once we've calculated this number, this 114.75, if there are any numbers in the data set that are larger than that, then that is an outlier. And we say it's an outlier. And we put a little asterisk in the box plot to show that that's an outlier. But 98 is the largest number in the data set. It's not larger than 114.75, and therefore 98 is not an outlier. Now, if 98, which is the largest number in the data set, is not an outlier, that means no number is a large outlier, right? Because if 98 isn't an outlier, certainly any number smaller than 98 would not be either, that are, bigger than the upper quartile. Now, we also want to check for small outliers that are along here, that are smaller than the lower quartile. So what do? Well, we take at 1.5 IQR, that 30.75, and the recipe says we subtract it from the lower quartile number. In this case, 64. 64 minus 30.75 is 33.25. And what does this say? What does this mean? If any numbers in the data set are smaller than this number here, which means it's to the left of that number, it is an outlier. It's an outlier. Well, 32 is smaller than 3.25. Therefore, 32 is an outlier. And we're going to actually put an asterisk there to indicate on the box plot that it's an outlier. Okay? And that's why the whisker only goes from the lower quartile down to 55, which is the next smallest number. And then nothing in between. There's a gap there between 55 and 32. And then we have this asterisk that indicates 32 is an outlier. So this is a way of displaying, from this 5-number summary, of displaying it through a box plot and also determining if any numbers in your data set are outliers. Right? This is a recipe for doing that. All right. So what I'm going to do is correct this, and calculate everything and then display it correctly on Canvas for you. I'll post it later today with the corrected numbers. All right, but in essence, this is how we do it. And typically on test number 2, I have a problem like this. I might even, instead of having you calculate the 5-number summary, I might give you a box like this and then ask you questions about it. Now, one thing we can do with the box plot is we can answer the following questions. We can say, all right, between 32 and 64, what percentage of the data is between 32 and 64? And your answer would be 25%, because the Q1, or the lower quartile, means that 25% of the data is less than that. Well, less than 64 would be any numbers to the left here, and that would run from 30 all the way up to, but not include, 64. So this would be 25% of the data between 32 and 64. Between 64 and the median, which is 78.5, is another 25% of the data. Between 78.5, the median, and 84.5, the upper quartile, is another 25%. And between the upper quartile and the maximum number, 898 in this case, is the last upper 25%. So this box plot splits your data into 4 quarters, or 4 equal pieces. All right. Now, let's test to see if this works. Remember, the upper quartile means that 75% of the data is less than that. Well, let's see if it's true. From the upper quartile to the median is 25%. From the median to the lower quartile is 25%. And from the lower quartile to the smallest number is another 25%. So 25 plus 25 plus 25 is 75%. So there is 75% of the data that's less than the upper quartile. If I ask the following question, what percentage of the data is bigger than, bigger or equal to 64, larger or equal to 64, what would the answer would be? It would be, well, 25 plus 25 plus another 25. That's also 75%, isn't it? Well, the lower quartile, 25% of the data is less than that, but that would mean that 75% of the data is greater than that, and that's true. 25 plus 25 plus 25 is 75. If we wanted to know how much data was inside the box here, it's 50%. How do we know? Because from the lower quartile to the median is 25%. From the median to the upper quartile is another 25%. That's 25 plus 25 is 50%. And by the way, we can say that the interquartile range contains the middle 50% of the data. That's another way of saying it, right? And because it's the middle 50% of the data, the interquartile range is not affected by outliers, is it? Because the outliers are going to be either really small or really large. And the middle 50% is the same, doesn't get changed by outliers. If this number 32 again was a 50, it wouldn't make any difference about this middle 50%. It'd still be the middle 50%. Okay. Any questions about the interquartile range and also how to calculate an outlier and how to display all of this with a box plot? All right, so everything I've just talked about will be tested on test 1, and also the final exam tested also. All right, so everything that I've just talked about definitely will show up on a test. Test number 2, and also the final exam will have questions like this. All right, no questions about that? Okay.
When is the first test? What's the date?
Well, I meant test 2. It's on the syllabus. I don't have it in front of me, but the syllabus has the next test. It's in like 3 weeks, I think, or something.
in our next quiz?
Yes, the next quiz will be on, actually, I'm going to make the next quiz next Thursday, not Tuesday, because I'm not going to be able to cover all of Chapter 8 today. And I'm going to start that, I'm going to start it today, but I'm going to continue with it on next Tuesday, and also Chapter 9 on Tuesday. So Chapters 8 and 9, which is the next quiz, the quiz will be next Thursday, not Tuesday. I'm going to make that change. All right. So that's that. All right. So that's it for this this particular problem set. I think it's a very good problem set. It teaches you everything, it summarizes everything that you need to know from this chapter. And again, I'll make the corrections and post this later. It's a good thing I didn't post it because of these silly mistakes that I made. All right. So what I'm going to do next is start the next Chapter 8, begin that, and then continue with that on Tuesday. All right. So here we're going to be talking about quite a bit about the bell-shaped curve. We talked about, a little bit about skewed left, skewed right curves, right? But the bell-shaped curve is the one that's used a lot in statistics. We're going to talk a little bit about it in general. If this was again, a regular statistics course, we would actually be doing many, many calculations using the TI-8384 calculator with the bell-shaped or normal curve. It's another name for it. But in this course, we're not going to be doing as many calculations, and it's not as calculation as intense as that other course is. All right. So let's look at this first thought question. It says the heights of adult women in the U.S. follow, at least approximately, a bell-shaped curve. What do you think this means? Well, I'm actually going to just give you because we're running out of time today, I'm just give you my own viewpoint in this. What it means is that quite a bit of the people are going to have heights that are close to the mean or median. All right. Most people will be near the middle, and then it will tail off to people who are very short, women who are very short, and then women who are very tall. So the gymnasts, the people who are very short, the professional gymnasts, they're going to be the ones tailing to the left, and then the adult women who are basketball players would be the tall ones, would be the ones tailing to the right, and then most women will be in the middle. Okay. What does it mean to say that a man's weight is in the 30th percentile for all adult males? Well, the idea of percentile, you might have seen this before. The 30th percentile means that 30% of the males weigh less than whatever this number is. The 30th percentile will be a weight, particular men's weight, and we would say that because it's a 30th percentile, the 30% of the men weigh less than that. That's one way of saying it, okay? 30th percentile. If it was the 70th percentile, it would be a bigger weight, and we would say 70% of the men weigh less than that weight, okay? Now, the 50th percentile is called the median. The 25th percentile is called the lower quartile. The 75th percentile is called the upper quartile. All right, we just learned about that, right? So those are those special percentiles. All right, the 25th percentile, the 50th percentile, and the 75th percentile, they're part of those 5-number summary. Then we have those other ones that are in between, like the 30th percentile. But the definition means exactly the same. 30th percentile, 30% of the males weigh less than that particular weight. Okay? Now, there's something called the standardized score. If we were weighing you, or taking your height, or some other characteristic, a numerical characteristic of you, that's called a raw score. Let me give you another example. If you were taking the SATs, now it used to be, I don't know if it's true anymore, But it used to be the SATs. Each section of the SATs would run from 200 to 800, for the math part and the verbal part. You would get a score. Let's say you scored 600 on the verbal SATs out of 800. The 600 is considered a raw score. Okay. But what they would tend to do is give you what's called a standardized score. Standardized score is where you would do a little calculation to convert that raw score into a score which you'll be able to compare yourself to other people who took that particular test. With weight or height, it's the same thing. So for example, male heights have a mean of 70 inches. Okay, let's assume that's true. And a standard deviation of 3 inches. Now remember, the standard deviation is an average spread of the heights in this case here. So the average spread between two heights is about 3 inches. That's what it's saying. Now, suppose female heights have a mean of 65 inches and a standard deviation of 2.5 inches. Suppose you have a man that's actually 73 inches tall. That person's standardized score is 1. Now, how did we come up with 1? Well, what you do is you take your score, your raw score, in this case 73 inches, you subtract the mean, and that's 3 inches, right? 73 minus 70 is 3. And then you divide it by the standard deviation. So this raw score minus the mean is the numerator of a fraction, and the denominator is the standard deviation. So 73 minus 70 divided by 3 is 1. What exactly does 1 represent? 1 represents the fact that this person who's 73 inches tall is 1 standard deviation taller than the average man. How do we know that? Well, the person who's 73 inches tall is 3 inches taller than the average man. But that 3 inches represents 1 standard deviation. 1 standard deviation is 3 inches. So we can say that that man is one standard deviation taller than the average man. Okay, 1 standard deviation taller. Now, because it's positive, I know the person's taller. If it was a -1, the standardized score, it would mean the person is 1 standard deviation shorter, right? For example, if the man was 67 inches tall, okay, 67 minus 70 is -3. And if you divide that by 3, that's -1. So a man who's 67 inches tall would have a standardized score of -1, and that person is 3 inches shorter than the average man. So the negative would tell you your raw score is less than the mean. The positive standardized score means your raw score is bigger than the mean. Okay. So that's basically what we're going to learn. All right. And then, of course, data sets, we talked about the shape of the histogram, right? In that example that I just showed you from chapter 7, where we had a skewed left shape, and then we have skewed right, and we also have symmetric. All right, so we're going to look at pictures like that. Sometimes, instead of drawing a histogram, they draw what's called a smooth histogram or a curve. All right, you can picture doing that, drawing a curve around the histogram. And this is called a frequency curve. All right, so this is frequency curve is for heights of British men in inches. Right. And then what's along the y-axis here looks like relative frequencies, doesn't it? Looks something like a relative frequency. These are percentages or decimals that represent the percentage of people at these various heights. We'll get to that in next time. But this curve is very symmetric, isn't it? If I draw a vertical line straight through the middle here, it would be, the left side would look like the right side. It would be a mirror image of the right side, wouldn't it? So this is called a normal curve, bell-shaped curve. Sometimes it's called Gaussian, but don't worry about that. There was a famous mathematician named Gauss who came up with this idea of this curve. But this is a way of representing the heights. Now, one thing that we do is that the average is in the middle here, right where it peaks. If you just drew a vertical line down, that would give you the average and also the median, because for a bell-shaped curve, the mean or average is equal to the median. So we could say 50% of the data is less than the mean only for this bell-shaped curve, this normal curve, and 50% of the data is greater than that. All right. So it's very special, right? Because the mean is equal to the median for bell-shaped curve. So we could say 50% of the data is less than the mean because the mean is equal to the median. They mention here that the area under this curve is equal to 1, So in other words, if we drew, we colored the area under the curve here above the x-axis, this area, and it goes on basically to negative infinity and positive infinity. But if we drew this area, it would be equal to 1. That's a special property of these curves. But it says not all frequency curves are bell-shaped. Okay, this is a case of I was talking about this before, of skew to the right distribution, right skew distribution. Notice most of the data is to the left. When we see the height here, it means there's a lot of data that is these lower values, and then it tails off to the right, which means higher values, but they're not as frequent, less frequent. So these are more like higher outliers out here. And that means that the mean is going to be bigger than the median. All right, this is the right skew. This is the distribution I was telling you about before, but now you can see what it looks like.
So would the median be 6? Because the
median will be near, yeah, that's a good question. Is it near? It's closer to 6 than the mean would be. It wouldn't necessarily be 6. Actually, the mode, which is the most frequent value, would be 6. My guess is the median is going to be somewhere a little bit bigger than 6 here, or maybe a little bit less than 6, but it's not exactly 6. But it's certainly nearer 6 than the mean would be. So that's a good question. Yes, it would be near 6, probably not exactly 6. The mode would be 6. Okay, that's a very, very good question. And I think we will stop right here for today. And we'll continue with this next time when we talk more about these normal looking curves. Okay. Any questions? And very good questions, very good comments today. Very happy with your responses. So it's very good. And again, Nika, if you could stay behind, anybody else wants to stay behind to listen to my explanation again about how to find the median, I'll be glad to spend a few minutes to do that at the end. But I'm going to stop the recording now.